which is the mass moment of inertia of this simply supported beam. And the beam, you can also treat it like a bar. So it's 1/12 over L squared over 12 plus 1/4, then this will give you 1/3. M times L times 1/3 of M times L squared. Right? So this is the first example we did, a mass moment of inertia. And we can actually calculate this value. And that just 1/3 of mass is 4 kilograms. And the total length is 3. I believe we had the information before. From here to here, this is 3 meters. So multiply by 3 squared. So this will give us just 12. And the unit is kilogram meter squared. So this is the mass moment of inertia at the center of rotation, IA. So we found this value. Next. So we're going to apply everything into here. So how do we do that? Well, we'll calculate the moment equilibrium. The free body diagram of this simply supported beam can be considered like this. That beam at here, and what are the forces acting on this beam? First of all, you have the weight, and this is 39.24 newtons, right? And of course, in response to the application of this weight, you had the reaction RB, which is 1/2 of this weight, and that is 19.62 newtons. One here. Of course, at the same time, you also have RA to be the same, which is also 19.62 newtons, correct? And we also have this 100 Newton acting like here. So we know that the application of all these forces will result in this dynamic motion, and which can be represented by the product between the mass moment of inertia at the center of rotation and with angular acceleration. So it's this term right here. So that's what we're going to do. We're going to relate all the forces, take all the moments with respect to the point A, and relate it to the product of mass moment of inertia at the center of rotation and its corresponding angular acceleration. And we can simply do this right here. Summation of all the moments, of course, which direction you like to assume to be positive. Maybe we assume clockwise. Summation of all the moments equals to IA times alpha. We'll do it like this. Now, before I continue, some of you may wonder that in this equation, I said summation of moment at any point equals to m times ag, right? Times x y bar plus minus m times ag times x bar plus ig times alpha. Why, when I put it down here, I only have one term, not 3 terms? Right? Down here, I have 3 terms on the right-hand side of this equation. 1, 2, 3. So when I put it down here, I only have copy 1. I did not copy the first 2. Does anybody know why? Does anyone know why?
Is it because X and Y bar are 0?
No, X and Y bars are not 0. At least for one of them, right? You have X and Y. Suppose this is X and this is Y. For the Y, X, Y, AGY, you're looking at X bar. X bar in this problem is half of the span, which is 1.5 meters. So X bar is not 0. Y bar is 0, correct. But X bar is not 0. So that's not the reason. Why? I actually copied just one term, not 3 of them, from this definition. Why is that? This is the important concept. Now, here's the answer. The reason why I only copy one term from here to here is because of the subscripts. Now, in the formulation, if you want to use a 3-term formulation, you have to find out 3 things. First, linear acceleration at the center of gravity, the x component. 2, linear acceleration in the y direction. 2, 3, mass moment of inertia at the center of gravity. 3. Now, but when I put it down here, did I use the mass moment of inertia at the center of gravity? Did I use it? No. What did I use?
The center of rotation.
Yes, I use it at the center of rotation. Therefore, this result is actually a derived result when you actually use it. This is just like what we said before, parallel axis theory. Mass moment of inertia at the center of rotation equals to the mass moment of inertia at the center of gravity plus m times d squared. And this d here is nothing but the product of these two. So the second term here actually accounts for the first two already. Therefore, when we write down the moment equilibrium, you can choose to go this way. You say, I don't want to find out IA. I just want to use IG, which is just this one. This is IG here. Now, but if you choose that, you will have to consider 3 terms on the right-hand side of the moment equilibrium, which may not be the good idea, right? Besides, we don't even know what is AGX with AGY. How can we use this? So we have 2 approaches. The first one is you have to find out the 3, 1, 2, 3, in order to use this form, or you find out the mass moment of inertia at the center of rotation, not at the center of gravity. This is IG, but this is IA. Once you move it to the center of rotation, it becomes just one term. Now, which way would you prefer? Definition or parallel axis theory? Which way?
Probably the parallel axis theorem.
I think most reasonable man would choose this, right? Why would you want to trouble yourself with finding the 3 terms in order to calculate this? Not to mention that you had to get the signs and or the directions of these moments correctly, which could be sometimes tedious. But if you calculate the mass moment of inertia at the center of rotation, then your moment equilibrium becomes only one term on the right-hand side of the equation, which is much easier. So that's why I have only one term, not 3. This is only a difference by the subscript, but the meaning is very significant. Okay? All right, so with this, and we can continue with our calculation. So I said the positive direction is clockwise. So we calculate the forces. Of course, how many forces we have? 1, 2, 3, 4. And you know the reaction A doesn't count because it's acting at the center of rotation, right? Doesn't produce any moment. So you have how many terms? 1, 2, 3. So we just do the math. These two will be positive. You can just say that 100 plus 39.24 is positive, right? Times 1.5. This one will produce negative moment. So it's become negative 19.62 times 3 equals to, now, what is the sign for the alpha here? Positive or negative?
Positive.
Yes. Positive or negative? Positive, right? Because the same direction as you assume to be the positive direction of the moment. So here it was going to be IA times alpha, and IA we already know is 12, so it's just 12 times alpha. Correct? So this is how we determine alpha. We have one equation with one unknown. Certainly we can find out the value of alpha. And the value of alpha is 12, positive 12.5 radians per second. So this is the first answer. Now, if you know the alpha, how do we find out the linear acceleration at the center of gravity? How do we do that? Well, the two different approaches, either by knowing the tangential and normal component, or simply by what we call angular motion. From angular motion, you know that if there's alpha here, and you know the distance, which is rg. The linear component at this point, which is ag, is just alpha times rg. Correct?